The primary motivation behind our work is that complex, real-world manipulation problems require the consideration of dynamic constraints. For example, both the payload and liquid transport problems impose constraints on end effector accelerations, while the use of impulsive actions is required to singulate objects in cluttered scenarios. In this work, we introduce a kinodynamic planner that quickly plans collision-free and dynamically feasible trajectories for a high degree of freedom system. This is difficult to do with current work since the simultaneous exploration of state and control space is slow for high degree of freedom systems. This is due to two main reasons. First, most existing work in kinodynamic planning is in the single query domain, which requires the reconstruction of the search tree for every new planning query. And second, simulation and collision checking are computationally expensive operations. To solve these problems, we present three contributions. First, we enable multi-query planning by pre-generating state and control space rollouts using the robot dynamics model. Second, we introduce lazy propagation and collision checking strategies to defer expensive computation until absolutely required. And finally, we present a planner called Lazy Bundle of Edges that leverages the first two contributions to plan collision-free and dynamically feasible robot trajectories. Our first contribution lies in discretizing our state and control spaces via Monte Carlo propagation. This generates an edge bundle where each edge is defined by a pair of start and end joint angles, a sequence of random joint velocities, and a randomly sampled time duration for which its control is propagated. Given an edge from the bundle, we perturb its start state by a maximum of theta, which defines the planner's search neighborhood. We then apply the same controls for the same time duration to each of these perturbed start states. This allows us to compute the probability that the end state will stay within the theta bound, which will allow us to continue a sequence of lazy propagations in the planner. We follow a similar procedure for computing the probability of collision when an edge is lazily propagated. Given these contributions, we can consider the problem of planning a robot trajectory between a pair of start and goal states. First, a candidate node is picked from the planning tree as one with the best F-score. Then the algorithm extracts all the bundle edges emanating from a theta neighborhood around this node. The edge with the best heuristic value and highest probability of lazy propagation is chosen. This process is repeated until the goal state is encountered, at which point a series of real propagations is performed along the lazy guiding path. We compare lazy BOE against several baseline kinodynamic motion planners, and demonstrate that our approach yields a statistically significant difference in initial time to solution, final solution cost, number of solutions, and success rate. Here, we show the execution of a kinodynamic RRT plan on a 7 degree of freedom robot arm. The simultaneous exploration of robot state and control spaces accounts for the changes in robot dynamics resulting from the additional payload. Next, we address the same planning problem using our method, yielding a more cost-effective solution by leveraging the inherent downward force exerted by the payload on the arm. In a cluttered scenario, it becomes necessary to use an impulsive action like poking to singulate the target object for further manipulation. This requires that the robot apply an impulse force on the group of movable objects to scatter them, which in turn requires the use of a kinodynamic motion planner. Thanks for listening.